Hello everyone. Now we will start with the quantum mechanics. So this is the quantum mechanics, the new topic. So here we are going to learn the basic concepts of the quantum mechanics and where all we are going to use that. What are the applications of the quantum mechanics? I'll just briefly introduce this topic to you people. So here we have the two terms. One is quantum and there is mechanics. We know very well what is the mechanics. The study of objects in the motion is called as mechanics, or we can call it as a dynamics. Now what is quantum that we are going to learn, or the quanta? Already have seen the packet of energy is a quanta. The such a kind of a things we are going to learn in this chapter. What is quantum mechanics? So it deals with the properties or the study of nature at the atomic scale. Okay, so it is a study or the study of a properties at atomic scale, or we can say the behavior of the matter and light, okay, at the atomic or subatomic scale. Atomic or subatomic scale is nothing but the electrons, neutrons or protons. Atomic scale is nothing but molecules, or in this, or the nanoparticles. Okay, the study of these, what is the momentum there, what is the mass, what happens when we irradiate the light to that, what is the transition from lower level, lower energy levels, what are the energy levels. Okay, these all consists in the quantum mechanics topic, right? We have classical mechanics topic. So before quantum mechanics, we were having classical mechanics, and still we have. So this mechanics, it is the called as Newtonian mechanics or classical mechanics. So this works on three laws, Newton's three laws. Newton has found it in 17th century, the three laws. Okay, we know that all the three laws very well. Okay, this works for the larger objects. Okay, the larger object which are not atomic. Okay, the larger object may be anything, that may be ball, that may be car, or the celestial bodies, planets and stars. It works very well to the all the larger objects, but it failed to explain at the scale of the atomic scale. At the atomic scale it fails. For example, you know that the third law, every action has equal and opposite the reaction. Okay, so that means what, let us say this is the wall, this is the wall, and when I hit the ball to this, and this will come bounce back. So this is the third law, which says, which will not go this side. Okay, so where there is a wall, this is, let us say this is a wall, right? This is a wall and it hits and come back. Okay, this will not happen to the electron. If I take an electron, and when it hits to some potential, we call it as a potential barrier. Okay, and it will not come back like this. Okay, if it has a sufficient energy, it will go, it is called as a tunneling, it will go beyond this. So these things will start happening in the atomic or subatomic scales. So this we call it as a potential barrier. Okay, it goes that side of the potential barrier. So this did not explain by these three laws or the classical mechanics. Okay, so it fails to explain these mysterious phenomenon at the atomic level. And and it did not explain what is a black body radiation, why black body radiation will happen. So we have the for the black body we have such a kind of a graph, why the nature is like this. Is there any theory which fits exactly the curve? No, it did not explain. And photoelectric effect, where we have particle and wave nature of light, and quantum effect, so which is says the X-ray photon, when it hits to electron and the incident photon are scattered like a collision, right? And emission of a line spectra, we have a band spectra. In the same way we have the line spectra, wherein the transition takes place in the material and it gives rise to the line spectra. So it did not explain, classical mechanics failed to explain these all concepts. So we have the new mechanics or new theory that is called as the quantum mechanics. So where all we use this, still we can use this. It's not like it's not valid means it's not like that. Now we are not using, we're using for larger objects. For smaller objects we have the quantum mechanics. So what are the applications of the quantum mechanics? So quantum mechanics has invented, because of the quantum mechanics we have the lasers, we have the diodes in the lasers, we have the transitions from the lower energy states. What are the energy states that can be explained only by the quantum mechanics, not with any other theory? And diodes, in case of diodes, what are the holes, how do they behave? And the transistor, electron microscope is another invention wherein we can have the images at the nanoscale. Okay, we there the electrons are hit to the target or hit to the object which we want to look at. It's the micro image, and it will give us the image of that particular object in the nanoscale. And whole nanotechnology is dependent on this quantum mechanics. At the higher level or the bulk level, the behavior of the material will be different, and at the nanoscale, when I take the same material to the nanoscale, its behavior start changing. For example, the gold is yellow color in the bulk. Okay, when I take its nanoscale or nanoparticles of the gold, the color starts changing of that gold particles. So that can only be explained by the quantum mechanics. We have magnetic resonance imaging, that is MRI, and in the distance applications we have nowadays the quantum computing or quantum cryptography. So many things we have coming up, computing which will be very easy and very faster by using this quantum computing. And the behavior of the conductors, insulators, semiconductors are all can be explained only by the quantum mechanics. So these are some of the applications. Now we will see the concept of photon, why they started using the word photon, and we will see where all they are using that. Now there was a black body radiation experiments were going on, and why the black body emits such a kind of a colors, or why it is this kind of a graph. Okay, so we know that the black body is nothing but which absorbs the all the radiations and start emitting all the radiations which differ with respect to the temperature. Okay, it's very simple, the emitted radiations. Okay, for example, if you take a block of a iron which can be, let us say that it is a hot body now, and which is emitting the radiations. Okay, so this is the piece of iron. Okay, this is hot now, this is hot now, and we know that the hot iron block will be red in color. That means what? It is emitting red color of light. So this is emitting red color light in all the directions. When I record this, okay, how do I record? Its intensity, what is coming out, its intensity versus what is its wavelength. If I record, then I'll get this kind of a curve. This black color curve is the experimental curve. So which is the radiation which is coming out from the black body. Okay, this black color is the curve of intensity versus wavelength, which is recorded from this black body. Right, this side it is intensity and this side it is a wavelength. Right, so this is, so always there will be two things, one is experimental and there is the theoretical background for that. So now we have the experimental graph, experimental curve. For that we should have the theoretical curve or theoretical background for that. Okay, so Wien, Rayleigh Jeans and Max Planck were working on that, and his findings, the Wien has he found that his equations or his theory only fitted till here. So his curve fitted till here. This is a red dotted line is a Wien's curve or Wien's law. His theory or his equations explained only in the lower region of the wavelengths. That means in the beginning it has explained on the in the beginning. After that it started deviating from the experimental curve. This is experimental curve and this is the Wien's law. Okay, it started deviating from the actual experimental curve. So it did not explain at the higher level of the wavelength. Only in the lower wavelength it has fitted. And Religions has explained his equations or his theory explained only in the higher level of the wavelengths. Okay, it did not fit it goes up here, so that it did not fit this curve, only it has fitted the higher level of the curve. Okay, and this also did not explain, and Wayne also did not explain the entire curve, whereas the Planck's has explained it very well. His curve fitted exactly to the experimental curve. Why he succeeded? Because he considered what all things are coming out, the radiation which is coming out from the hot body or the black body. He has considered it as a uh, photon, or we can call it as the quantized nature of that. It's a packet of energy which is coming out from the black body. Since he has considered that and formulated with his mathematics, he succeeded to fit this curve completely, right? So this is the curve which is the Planck's law, and since then we are using this as a quantized nature, or the quantum, or the quanta. We can call it as a packet of energies which are coming out, and those are called as the photons. And further, in 1905, it is evident by the Einstein's photoelectric effect. For this invention, he got the Nobel Prize in 1905. And what he said is, when photon hits to a metal surface, so metal, we know that there will be free electrons. That's why the metal conducts the electricity. So we know that the metal consists of electrons, and when the photon hits to the surface or to the electrons, electron will eject. That means this is the photoelectric effect. So where he has considered this as a photon hitting to the electron, and electron is ejecting, coming out from the metal surface itself. Okay, this is the support for this his Planck's law, that he has considered this as a quanta, or quantized nature of that of energy. After black body, then the people started thinking about the light. What actually is light? Okay, the light which is coming out, or the radiations which are coming out from the black body, are quanta, or the quantized energy. Then what is the light? Okay, light should be something else, or whether light has the wave nature or the particle nature. So that's why they started thinking about the light, the nature of the light. Okay, now they came up with the final conclusion that light has the dual nature. It has got the particle nature also, and it has got the wave nature also. So for that we have the evidences that the light has the wave nature, we know, and people agreed that light has got the wave nature. And for that wave nature, what are the experiments? The experiment for that are the interference and diffraction. So from these two things we can say that the light has got the wave nature. So what is interference? Let us consider the source of a light. Let us say this is source of light, and when it is incident on the screen, so let us say this is a laser light itself, and then we can say there is a light falling on the screen. Okay, so when we have two sources of light, okay, so when we have two sources, this is one source and this is another source, that means there are two slits for this. Okay, there is only one slit and light is falling on this screen. Now we have two slits. Why we have two slits? To make the two sources of we call it as a coherent sources. That means wavelength will be same there. And so these are the coherent sources, so that we have the interference there. Fine. So when we have two sources here, and when these are interfered, we will get this kind of a fringes on the screens. So we will get the bright fringe, and then dark fringe, bright fringe, dark fringe, like this we will get the patterns on the screen. So this is because there is a interference happening between the waves. So this happens only in case of a wave. That's why we can say the light is a wave. The nature of the light is wave. Why? Because it is interfering here and we are getting the bands here. Okay, so these are called as interference fringes. And similarly we can have the bending of light, that is a when light hits to a corners, then we will get the, these are the diffraction patterns. You all have seen the laser experiment that we have the these kind of a patterns, and we measure the distance between each these fringes, and we calculate the wavelength of the laser light. That is all because light has got the wave nature. Okay, so you all have learned this in the previous classes, that how interference will happen. Briefly I'll explain this. When we have this source, this one source which is split into two sources to get the same wavelength, that means to get the coherent light. Okay, so here this let us say this red line indicates us the crest, and this dotted line indicates the trough. This is crest and this is trough. So this is the wave of a single source. Okay, this is the wave of a single source. This is like this. This is a crest, this is a trough, this is a crest, this is a trough. Like this it is moving. That means this is indicated with the this line. Okay, solid line. And this trough is indicated with the dotted line. Okay, so that we can draw this in two-dimensional paper like this. This is a crest, this dotted line is a trough, this is crest, this is trough. Okay, so now this is the wave, this is a crest and this is a trough. This is one wave. When this is interfered with another wave, what happens? This is crest and this is crest. When crest falls on that, what happens is intensity or the amplitude will increase. Okay, so if it is a reverse, if it is reverse, that means when we have this is the wave which is falling on the exactly reverse of that. When crest falls on the trough. Okay, so that what happens is when crest falls on the trough, what happens? The resultant will not get anything. The resultant will be 0. That means when crest falls on the crest, when trough falls on the trough, what we will get is we get the bright fringe. We get the bright fringe. When the crest falls on the trough, what we will get? We will get the dark fringe. Okay, so this is a thing which is happening here. This is the crest which is falling on the crest. Okay, at this point it is falling and it is giving rise to the bright fringe. So here it is the solid line which is falling on the solid line. That means the crust is falling on the crust. Here also the crust is falling on the crust, and similarly we will be having so many the light waves which are falling on each other, and the effective of that will be bright fringe here. When crest falls on the trough, so the effective interference will be the dark fringe. The same thing we will have for each of the points. We will have this dark fringe, bright fringe, dark fringe, bright fringe, like that we will be having the patterns. The same thing is true for the diffraction patterns also. So this is called as the interference and the diffraction. This happens when we have the wave nature of the light. Okay, this happens only when the light has got the wave nature. Okay, so this is the wave nature of the light. Okay, this is in brief. I have explained this is not necessary actually. In brief, this is the wave nature of the light. Okay, so now we have the evidences for the particle nature, right? So to prove that light has the particle nature, we have photoelectric effect and the quantum effect. Okay, so we have here Einstein has explained that when it hits to the metal surface, electron is ejected. That means photon is treated as a particle over here. Here what is happening? The collision is happening. This is hitting to this and it is knocking to this electron, and electron is ejecting. This is the particle nature. And same thing will happen over here. Here when I consider this X-ray photon, actually this is X-ray photon. When this X-ray photon hits to the material, and that consisting the electron is scattered. Okay, this is scattered here, and this photon is scattered this side. Okay, the scattering happens only when it has got the particle nature. That means light has got particle nature. That means we consider here the photons. So when photon is hit to this, okay, and this is scattered this side with an angle phi, and this is photon is scattered this side with the angle theta. Okay, whereas this has the higher wavelength, this has the smaller wavelength. And this is these are the evidences, these two are the experiments for the particle nature, and these are the experiment for the wave nature. So this is double slit experiment. And or you can take the Newton's ring also. You all have seen, in case of Newton's ring, there are so many rings which are having the bright ring and dark ring, bright ring and dark ring, that we have seen and done the experiment. Okay, in the same way we have this interference pattern and diffraction pattern. This happens because of the wave nature of the light, and this happens because of the particle nature of the light. In 1924, Broglie came into the conclusion that, looking at these experiments, he said that this is the matter wave, and he given the name as the matter wave. Because of this dual nature of light, he has given as matter wave, and its wavelength is h divided by p, where h is the Planck's constant and p is the momentum, that is mass into velocity. Now, de Broglie has said that wave and matter, and he said that it's a matter wave, and he found the lambda, that means the wavelength for that matter wave. So now what he considered is, he considered an electron. Electron is particle also, and it behaves as a waves also. Okay, he has considered the electron in electric potential V. That means it is accelerated electron. What is the aim of this derivation? This derivation aim is to find out the relation between the lambda, that is a wavelength, that is de Broglie wavelength, and the kinetic energy of that particular electron. So that electron is considered in accelerated potential, that is capital V is the potential of that. When it is accelerated, it gets the velocity, that is a small v, and it gets the kinetic energy. Okay, that kinetic energy can be written as half mv square, and the energy associated with that electron is E into capital V. Capital V is a potential, or we can say the voltage applied there. This is a potential, and this is the velocity of that particular electron. So now let us equate, let us say this is equation number 1 and this is equation number 2, and this will be EV is equal to, it is half mv square. Okay, what we want the relation between this lambda. Okay, where is lambda term in this equation? There is no lambda term in that equation, but we know that this p, that is momentum, is equal to mass into velocity. Okay, let this p is equal to mass into velocity. So we have to replace this mass into velocity by this one, so that, so we know this p is also, the p is given as, it is h divided by lambda. There is lambda here, so we have to relate this, we have to bring in this lambda in this equation, and we have to find out the de Broglie wavelength. So that to replace this, let us square this both sides, so that this is squaring, this is m square into v square. Okay, so we have to replace this. That means this is m v square. I'll take this m this side, so that this is p square divided by m. So what is the value of this? The value of this will be p square divided by m. So that equation number 3 will become, okay, now let us write equation number 3, that is E into capital V is equal to, it is half p square divided by m is the answer for that. Okay, now what we should do, we have to replace this p by this this equation, so that, so what we have here, let us take this all the terms this side. This is 2 m E into capital V we remained with this p square this side. Okay, and p is equal to square root of 2m e into v, right? Then let us substitute this. P is equal to h divided by lambda. Okay, that means this is h divided by lambda is equal to square root of it is 2 me into v. Okay, so that lambda is equal to, what's the value of lambda? It is h divided by square root of it is 2 me into capital V. So this is the de Broglie wavelength, or you can say the relation between this energy and the lambda. Okay, here this m is the mass of an electron, and this E is the charge of an electron, and V is potential is applied. H is a Planck's constant. So all the terms are constant except this potential. The potential can be varied. If potential is high, the acceleration of the electron is going to be more. So that this is the only one thing which is variable over here. Okay, which depends on what potential we are applying or what voltage we are applying to the tube. Okay, so that I can take this 1 divided by root V, and these all constant terms are there. Okay, so these are the constant terms, and this is the lambda. When I substitute the value for this h, value for m, value for e, that is a charge value, no, this is not there. Okay, this we have taken out, and when I substitute that, I'm going to get this lambda. Okay, I'm going to get, so that you can substitute the values as 1.226 into 10 to the power minus 9 divided by this as it is. So the unit of the wavelength, it is a length, that means it is in the meters. Okay, this is the unit, and till here you can solve the derivation.